Hello ladies and gentlemen, welcome back to another video of the Azimuth. Today we'll be trying to make the smallest ever solar system. And we're going to do that by starting off with this. We're going to make it 6. And then we're going to turn off, you want to turn off calculated radius. Because when this is on, it's going to do basically like this. Like for example, say I'll make this twice the size, it's going to increase the mass. So you really want this, the calculate radius off. You want that off. And then what you do is you actually shrink the star again. This time it stays as the radius. So that's good. But maybe it's best if you actually lock it. And you can actually see the size of the star. It's so tiny. It's such a tiny star. And then of course it bounces back up. But we're going to actually decrease that. Increase that to say 2900. Basically this thing is going to be astronomically small. Hopefully that doesn't screw around with the... It shouldn't really. Basically this is going to be the smallest... Well, I say smallest. Let's actually make this even smaller. So we're going to start off with the inner planet. We're going to start about here. And we're going to make it have an elliptical orbit. Now, what is an elliptical orbit? Well, an elliptical orbit is when the orbit is not round. And that's just tearing itself apart. Okay. So let's actually remove all these chunks, and then let's make the habitable zone of the star bigger, so that we don't run into that problem. So let's put it around, say here, and it still tears it apart. Okay. Let's make the star, say 45,000. Okay? Keep that in mind, people. 45,000. Is that going to tear it apart? No, it doesn't. That's good. That's superb. That's exactly what we want. We don't want it to tear itself apart. So now, have it as an elliptical orbit. Make the orbit slightly smaller. And hopefully that doesn't tear it apart. No, it doesn't. So when it gets to the... There you go. And then you want to lock it in place. So... So when you land on the planet's surface, slow down time just a bit. It should look like that when you see, as the because the planet's spinning slower when it comes into its closest approach to the star looks like it reverses its direction for a bit. It will eventually set, but it's going to take a bit of time. So, we've got that planet. We're going to have to increase the habitable zone size a bit. This planet is... It's pretty large. Not really a big iron core. And then we're going to have this planet here, which is going to be a absolute beast of a planet. This planet's gonna be big. So that's a big old planet right there. That's a big one. But instead of being tidally locked, what we're going to have it as is we're going to have it to have a ever so slightly longer rotation than the orbit. You know, kind of like how Venus has a slightly longer rotational period than it does orbit. Yeah, that's what this planet is. Right, next planet. Now, put it there, like that. This planet is also going to be fairly large. .1. So this planet is also absolutely massive. The surface gravity is, because Earth's is like 9 meters a second. This is 28 meters a second, so it's a big planet. But this planet, unlike that one, that has a rotation period of 15 hours, this one has a 6.92 hour rotation period, or 24-hour period. So, we've got 3 extremely close planets. Like, they are super close. Very, very close planets. With a very, very tiny star. I mean, this star is tiny. It is a tiny star. It's smaller than Jupiter. That's what makes this planet awesome. I'm thinking I'm correct, it's... yeah. I mean, Pluto looks huge up against this thing. Looks absolutely massive. I mean, normally you would think, oh, a star wouldn't be this big. It's actually quite large. I mean, if you compare the size of these rocky planets to the star, you can definitely see the difference there. Okay, so next. This planet, maybe a little bit more out. I mean, right now it takes nearly 1.5 days to complete an orbit, which is not bad. Not bad at all. We're going to put in another rocky planet, but this time, if we put this rocky planet into a sort of a elliptical orbit, and then put this one into an elliptical orbit, and then this one is definitely going to be an elliptical orbit. Inclination of 8 degrees, and there you go. So this one is also going to have a pretty quick rotation. Rotational period, say 12-hour rotational period, but it's also going to have quite the axial tilt, 47 degrees. But the benefit of this is that it's actually going to have some water, and of course an atmosphere. So we need to put an atmosphere on this planet. So 1.01 bars. This planet is relatively small. So if we make this planet as, say, if we half it by 1. So let's have a look. If we actually make the planet, say, 0.6 times the mass of the Earth, but make the atmosphere bigger, 5 times the atmospheric pressure. And what we are going to do is boiling point is 153 degrees, which is really good. Greenhouse effect is 33. What's the average temperature? Surface heat capacity, let's turn that up. Turn it up again. Again. And again. And again. Oh wait, hang on, I think I've done it wrong. Let's have a look. The energy required to raise the temperature of his body. Let's put that to 10 degrees and see if that rises. Alright, so it stayed around the 5 to 10 degree mark, which is really good. And this planet is not too big. It's a tiny bit smaller than Earth. So look, what's the atmospheric pressure? .15. That's half that. So 14 degrees Celsius. And this planet's not looking too bad. Energy absorption rate, energy radiation rate, energy absorption, stellar power, atmospheric power, tidal power. So, because this planet's on a elliptical orbit, how close does the moon have to be? The moon doesn't have to be that close. So if we make the moon how big is it moon-wise? 3 moons. A few orbits. No. Let's make this smaller. Targeted lock. Oh god, it is on elliptical orbit. I do not need it on elliptical orbit. Targeted lock it. So how much power is it getting now? So if we change the axial tilt to 23.5 degrees, that's a massive moon. That's an absolute gigantic moon. Surface energy absorption rate should be going up in temperature wise, but it's dropping, which is not the ideal thing. Anyway, can't this thing have like city lights? So it can. So this thing is going to have city lights, that's good. So if we tidy it up. So this moon is basically, it's completely made out of iron, isn't it? Yeah, it is. Very close moon. Very, very close. Right, okay. Okay, okay, okay. Um. Let's put a gas giant here. Let's make it stupidly big. And then we're going to reverse its orbit. Reverse. Now hopefully this doesn't disturb the planets in the inner solar system too much. If it does, then boo-hoo. Okay. Times and half it. Chart. Yeah, it's practically the same size. Now you got to take into consideration that the Onon planet takes nearly 35 days to complete one orbit. That's faster. I think that's just over twice as quickly as Mercury around the Sun. So if we compare the size of this to the Sun, this star is tiny. It is a tiny star. It's an absolute. It's a mega dwarf, or it's an ultra dwarf. So how is our planet and moon doing? They're doing pretty well, actually. Inclination, let's put it as 1.6. And then this planet is going to have a few large moons. I mean, of course, they're going to be icy. Very icy worlds. And they're going to be tidally locked as well. Tidally lock, and tidally lock. And because they're made out of ice, what we're going to do is we're going to actually turn this down to only 433. So what that means is that stellar power, 303 terawatts. Tidal power, 160 terawatts. Absorption rate, 400. We're gonna turn that down a little bit more. And then, we're gonna actually shrink the orbit of this moon, and then make it have a slight elliptical orbit. And then this one's gonna have a ever so slight elliptical orbit as well. I mean, that is just an absolute amazing feat. I mean, that star is obviously extremely powerful. Very, very powerful star. Actually, what we're going to do to actually make this look like a realistic solar system, we're going to actually turn the to 1 and then turn this up to 3. So it lasts 3 times longer than normal. And then we should start to see some solar flares. And the moon is still there, so that's good. I'm not seeing any material in orbit. This star should start to flare in a minute. Rotation period 4 days. Turn that down to 2. Speed up time. Where's the 4th planet? It's around here somewhere. There it is. Come on, star. No, it will start flowing in a minute, so we'll give it a bit of time. Let's have a look what these rocket planets are doing. Not rocket planets, icy moons. So this is the closest one, correct? Yeah, it is. It looks more... It really does look more like a realistic moon. I mean, this planet has a axial tilt of 47 degrees, which means that that planet is gonna have wild storms, absolutely wild storms. And this planet, because it is closer to the star, these moons should not stay in orbit, but there is always the possibility, they are becoming more elliptical, there's always the possibility that these moons can actually swap orbits. And if that's the case, then that'd be awesome. But what we're gonna do is we're gonna actually make this moon as the biggest, as 3 moons. Actually, we'll make it bigger. Make it 5 moons. We can make it as an icy one. And I'm going to make this one as probably the smallest at 1 moon. And I'm going to make this one the 2nd biggest. so slightly smaller than the first moon, and then we're going to make this moon, wherever it is. Moon. We're going to also make it quite large as well. So the smallest moon here. So we're going to actually make it tiny lot. We'll make this moon tiny lot, this moon tiny lot, and this one tiny lot. So it's quite remarkable that these moons are staying in orbit so... Oh, hello. That's a very large flare from this star. Let's see if that has another large one. It's just a normal size flare, which is growing quite large. Okay, it's actually encasing the entire star in a flare now. The entire star's erupting, which is really not good news for these inner rocky planets. I mean, this planet should be okay. Should. So the magnetic field, it keeps on saying that the magnetic field is actually getting bigger. Magnetosphere. The next inner planet is going to have quite the powerful magnetic field as well. It's only going to be 4 gulfs. 0.4 gulfs. The inner planet, the innermost, is gonna have what some would describe as a partial field. Okay. So this system is quite compact. So anyway, guys, I'm gonna end the video here. I hope that you enjoyed the video. If you did enjoy this video, give it a thumbs up. If you didn't enjoy this video, give it a thumbs down. Put in the comment section if you would like to see, you know, a whole series of this. Because I'm hoping to not just create one system, but create like a collection of systems within one simulation. Anyway, guys, I'll see you in the next video. Peace.